Right. Welcome back. Our next speaker is Benjamin Lenz, then from Sorbonne Université de Sorbonne. And he's going to talk about spectral functions of strontium iridium oxide from cluster dynamical mean field theory. So as soon as you're ready, you can start. Yeah.
Okay. So I will start. Thank you very much for the kind introduction. And I would also like to thank you and the other organizers for giving me this possibility to present, as the previous speakers, a mix of some of the research I did over the past years and a hopefully pedagogical introduction of the main tool that I'm using for these kind of studies, namely cluster dynamical mean field theory. Okay. I just have to figure out how to. Okay, that's better. So just to give a brief outline of the next 25 minutes. First of all, I would like to motivate the very concrete example that I'm going to show, namely strontium iridate, to say why it's interesting and why it is actually not so typical, strongly correlated material. Then I will apply one of the standard techniques that we heard about yesterday and also today, namely density functional theory. And I will also explain why we have to actually go beyond that by applying strongly correlated methods. And in the second part, I will introduce this technique, dynamical mean field theory in a nutshell, and also to explain how to extend it in order to motivate the technique that we are actually using for studying spectral functions of strontium iridate. So in the very last part, I will show some examples, some results we obtained, and also show some limitations of the type of model that people usually consider here. But let's start with strontium iridate. So on the left side, you see the crystal structure of strontium iridate. As you can see here, the brown atoms are actually iridium, the red ones are oxygen. And so you realize that this material is actually made up of nearly perfectly two-dimensional layers of iridium oxide that are nicely spaced by strontium atoms in between. So why is this interesting for a theoretician? Well, if you look at the iridium atoms, you realize that they are in the iridium 4+ state, which means that you have a 5d5 configuration. So you have 5d electrons that are concerned. And what I plot here in the center is the radial distribution function for 3d, 4d, and 5d orbitals. So 3d orbitals you might be used to from cuprates, for instance, for copper oxides. And you can directly see that for 5d electrons of iridium, we have a way more extended orbital. So we have possibly very non-local physics that play a key role here. Furthermore, you can analyze the Coulomb interaction, so the electron-electron interactions of this material, and it turns out that these are quite modest, which means that they are roughly of the order of the bandwidth of the system. So from this information only, you would assume that this system is actually a correlated metal. Now, as you can see in the bottom panel, by now we can actually synthesize quite pure and quite clean single crystalline samples of strontium iridate, which allows to do a lot of different experimental studies on the system. The very first thing which you usually do is resistivity measurements. So what I show here is actually the resistivity as a function of temperature. And if you focus on the red curve, which is the pure strontium iridate sample, you can see that this sample is actually not a correlated metal, but a rather nice insulator, which is a bit contradictory if you only consider the modest Coulomb interaction and the non-local character of the system, which means that we're lacking an information here, which is the strong spin-orbit coupling. So iridium is a quite heavy element, which means that we have to consider spin-orbit coupling on top of the Coulomb correlations, which renders the system a so-called spin-orbit Mott insulator, which has a quite specific, peculiar ground state. Furthermore, it turns out that if you cool down the sample below the Néel temperature of 240 Kelvin, the system becomes a canted antiferromagnet, and this means that at room temperature, we have a paramagnetic insulator, and only at very low temperatures, the system is antiferromagnetic. Why is this interesting also from an experimental point of view? Well, I said it's insulating in the pure composition. However, on the right, I replot the same figure as before. This time, there's also additional curves for the doped sample. So if you replace strontium by lanthanum, you effectively electron dope the sample, and it turns out that at a sufficient doping, the system becomes metallic. So this is roughly around 4%, which you need to add. However, although it is isostructural to another family of materials which are superconducting, so this would be the superconducting oxides of the lanthanum cuprate family, this system stays metallic. It does not become superconducting. As I said earlier, we can today experimentalists can actually investigate very pure and clean samples, monocrystalline samples. So for instance, you can apply techniques like angle resolved photoemission spectroscopy to obtain spectra like the one shown on the left, where you can actually access the band structure of the system. Furthermore, you can, this is now on the left, a plot for the pure sample. You can have a look at the equal energy cut along, for instance, 200 millielectron volt. That's the blue line that's shown here, to have also an idea of the structure in the K plane. And this is what is shown on the very left panel in the center. Once you start to dope the system, this actually can also be investigated at the Fermi energy, where it then becomes the Fermi surface for the metallic system. So on the right, this is an example for 5% lanthanum substitution. There we're already in the metallic phase, and you can see structures that you know from the cuprates. So you see this pocket, this lentil-shaped pockets around the pi half point, which is very similar to what you know from cuprate superconductors. In cuprate superconductors, there's another feature which is very important, namely the so-called pseudo-gap phase, which means that as a function of the momentum of the wave vector, you can actually have regions, for instance, the antinodal region, where you have a depletion of the spectral weight at the Fermi level. So this is a very peculiar phase that people also hoped to find in strontium iridate, and this was also for us one of the main reasons at the beginning to study this system. Now, when you start to study such a system, for us, the very first step would be to look at the structure. On the left, once again, I show the structure of strontium iridate with these nice two-dimensional iridate planes that are then also shown on the right. So there I showed two neighboring layers along the C direction of these iridates. You see that the iridium oxygen octahedra are actually tilted, so they are rotated clockwise and anti-clockwise by roughly 11 degrees, which means that you have, due to this tilting, two different configurations of the iridium atoms. This means that you have a further symmetry lowering as compared to, for instance, the unrotated system that you would have for the cuprates. For us, it's only important to note that due to this reduction of the symmetry, you actually have a doubled unit cell, and so a reduced Brion zone. And this is actually the red reduced Brion zone that I will refer to in the remainder of the talk when it comes to high symmetry points. Okay, so the first thing we want to do once we know the crystal structures, actually we want to do density functional theory, which is very successful. Here, however, I would like to remark that in addition to the ligand field, to the crystal field that you usually consider, you also have to consider the spin-orbit coupling. This means that if you would only consider the neighboring oxygen atoms, you would have a cubic symmetry, which means that the 5d electrons would be split into a T2G and a EG manifold. On the contrary, if you would only consider spin-orbit coupling, you would rather split these 5d electrons into J5½ and J3½ states. Here, in the very specific case of strontium iridate, it's quite interesting because you see that if you combine both, you obtain nearly unchanged EG states, which are empty, and so-called J-effective 1½ and 3½ bands. This is actually what you also directly obtain from DFT once you allow for spin-orbit coupling. So this is now the band structure as calculated with DFT as a function of the wave vector k for a path along certain high symmetry points. You see 3 different bands which are color coded. So here we coded the J effective 1/2 band in blue and the 3/2 bands, J effective 3/2 bands in yellow and in red. So you can see that you have mainly one band which is important for the low energy physics, namely the blue one, the J effective 1/2 band, which should be nominally at least nominally half filled. So this is nice, but once again, DFT would tell us that this system is actually metallic. So once again, we're missing an important information, which, as I mentioned earlier, is actually the Coulomb correlations. So the electron-electron interactions, which are very strong and which are not properly treated in DFT. So what we want to do now is actually to take this DFT calculation as a start in order to construct an effective low energy model for this J effective 1/2 band. And then we will add on top of that explicitly electron-electron interactions. This is actually the part that was mentioned in the previous talk already. So we take the Hubbard-U limit, which means that we will add explicitly a local interaction for 2 electrons with opposite spin. So this is what we call a Hubbard-U term, and the model that we retain is a 1 orbital Hubbard model. This is still a model which you cannot solve exactly, so we have to apply approximative techniques in order to obtain a result. And what we hope to obtain is actually that the J effective 1/2 bands will be split such that we obtain a gap and explain the insulating behavior. So the technique that we're going to use is so-called dynamical mean field theory, which I will explain the next few slides in a nutshell. Of course, for all the details, please have a look at the reviews. I've listed 2 of them here, one for the technique itself and one for the rather material realistic applications. So the main idea of dynamical mean field theory is to replace the many-body correlated lattice system, the full system, by an effective atomic site that is then embedded in an electronic reservoir. What I mean by that is that you take a single site, a so-called impurity, which you then couple to a reservoir. That means that you allow electrons from the reservoir, from the bath, to jump onto the site and to interact locally on the site. So for example, what's shown here in the cartoon picture is as a function of time, the occupation of this impurity. So electrons, for instance, electrons of a spin up can hop onto this site. At a later time, a second electron of downspin can also hop on the site, and then we have to consider explicitly the Coulomb interaction between them. So one step of DMFT is actually mapping the many-body problem onto a local impurity problem, but the true approximation comes by the fact that we replace the lattice self-energy, so the quantity which contains all the correlation effects, by a purely local quantity. So we ignore all the momentum dependence. You can formalize this by this sketch on the right. So you want to establish a self-consistency equation between the impurity model and the local part of your full lattice model. To put this into equations, you can establish a full flow diagram, which is shown on the left. So you start with a certain guess of the self-energy, of the local self-energy. You calculate the central quantity of the full theory, which is the so-called Green's function, so the propagator of electrons in the lattice in the end. And then you will only retain the local part of the lattice Green's function in order to construct an effective bath, which you then solve on the level of the impurity solver. This impurity problem will give you a local impurity self-energy, which you will plug into the loop in order to recalculate the Green's function of the lattice and continue with this so-called DMFT loop. You stop once you have self-consistency, which means here that actually the local lattice Green's function is identical to the impurity Green's function. The important and costly part here is actually to solve the impurity problem. This is something you can still not do exactly analytically, so you have to use approximative techniques, so-called impurity solvers. I've just listed a few. They all have advantages and disadvantages, but generally speaking, this is the important and the costly part. So what are the main results and what is the big success of DMFT? The big success is actually that it can capture the phase transition from a metal to a Mott insulator as a function of the electron-electron interaction strength, which we parameterize here by U. So at the weakly correlated regime for very small interaction strength, we obtain the density of states, which resembles the band density of states. So this is a nice result. In the other limit of very strong electron-electron interactions, we have the so-called Mott insulator, which means that we split the density of states into two Hubbard bands, which are separated by a gap roughly of the order of U. And in between, we have a more complex spectral function where we have quasi-particle bands at low energy. So this is this very specific Kondo resonance signature right in the center. And you also have Hubbard bands. And then as a function of the interaction strengths, you transfer spectral weight from one to the other. So this is a technique which works really nicely at large coordination number. In other words, you can show that at infinite dimensional systems, this would be an exact technique. At three-dimensional systems, this also works nicely, but here we want to apply it to two-dimensional or quasi-two-dimensional systems, namely to strontium iridate. So how can we actually include non-local fluctuations, which are supposed to be important for these materials? There are in principle two different schemes in order to go beyond DMFT. One would be so-called diagrammatic extensions of DMFT, where you explicitly take into account in some way or the other the electron vertex. Here, however, we want to use a different approach, which are so-called quantum cluster extensions of DMFT. So the idea here is not to take a single atomic site, that's an effective atomic site which replaces the lattice, but rather a cluster, and to embed the cluster then into an electronic reservoir, into a bath. Thereby you include short-range, non-local fluctuations that should be very important for the kind of system that we are studying here. So let's return to strontium iridate. Remember, we have motivated a one-orbital model that describes the low energy physics. And once you apply now to this model a Coulomb U-term, a Hubbard U-term, and solve it with cluster DMFT, indeed, you can split this J-effective 1/2 band. You obtain an upper and a lower Hubbard manifold, and they are separated by a gap. So indeed, you can explain the insulating behavior of strontium iridate. With this in mind, just want to remind you that actually when going from dynamical mean field theory to cluster approaches, we replace the local site problem, which is sketched here, which amounts to a single site coupled to a bath, by a cluster problem. So here for DMFT, we have to restore the translational invariance of the system, which is usually done by a self-consistency condition. However, depending on the cluster you choose, for instance, here I will show results for a two-site cluster, very minimal cluster you can think of. You also have to restore the point group symmetry, because suddenly you realize that you can actually have two different orientations of this two-site cluster. So you also have to restore the point group symmetry. However, I would like to point out that this does not increase the unit cell, since you can regroup the 4 iridium atoms of the system into 2 oriented dimers. Okay, so let's have a look at a few examples and a few results. So what I show here is actually the spectral function on the left for undoped strontium iridate. You can identify on the top, in the empty part, in the whole part of the spectrum, the upper part of the J-effective 1/2 band. You also have the lower part of the J-effective 1/2 band and the 3 half bands, which are completely filled. This you can then, this is the nice part about the spectral function, directly compare to angle-resolved photoemission spectroscopy. This is what I show on the right, which actually shows remarkable agreement. However, to see this, you have to consider actually a superposition of the 2 Brion zones that I show on the right. The reason is that in the calculation on the left, we did not include so-called matrix element effects, so effects of the polarization of the photons with certain interaction of the photons with certain orbitals, which is very crucial if you do the experiment. This is why you should think of a combination of the 2 Brion zones and compare it to the calculation. If you do so, you can actually directly also attribute certain orbital content to the spectra. For instance, in the first Brion zone, you realize that you see mainly contributions from the J-effective 1/2 band, whereas on the right, you see nearly only contributions from the 3/2 band. Now, just to convince you that it's actually a good agreement between the calculation and theory, I will show on the next slide equal energy cuts in the K-plane at 250 and 500 milli-electron volt of the spectral function. This is what you see here on the left and on the right. For both figures, we show on the left the experimental data and on the right the theoretical, so the calculation. You can see that overall we capture really nicely the spectral function. You see slight deviations when it comes to the difference between the first and second Brion zone. This is exactly the difference of including or not including matrix element effects in the calculation. But apart from that, we have nearly perfect agreement between theory and experiment. Here, I would like to point out that these are actually measurements done at room temperature and calculations done for
5 more minutes.
Okay. For the paramagnetic phase, you can redo the same type of calculation also for an antiferromagnetic phase, which I have not the time to discuss here, but you can convince yourself that this also results in good agreement. So far, I've shown spectral functions for the pure sample. You can also electron or hole dope the samples, which is shown here. You can once again identify the J-effective 1/2 and 3/2 bands, but this time we have actually a metallic phase, which you can see by the crossing of the Fermi level via the J-effective 1/2 band, which will then result in the Fermi surface in pockets, actually. So this is what I show on the next slide. On the right, I have once again ARPIS results, so experimental measures, and on the left, I show the result of our calculation. Once again, we capture the main features, which are these lentil-shaped pockets around the M point, around the pi half point. We can go even one step further and investigate pseudo-gap-like features of the spectral function. On the right, I show the measurements. On the left, I show our calculations. And once again, we can capture these kind of features by looking at the symmetrized spectral function. Even when we look at hole-doped samples, so for instance, you could replace the iridium with rhodium atoms, which effectively corresponds to hole doping. You can once again investigate the spectral function, which works rather nicely. And also when comparing the Fermi surface, we capture most of the features. So far I've shown you that actually calculating the spectral function with CDMFT produces nicely the experimental results. However, we always considered a one orbital model on top of which we applied a Hubbard U-term. So what is actually the limitation of this approach? Is this always sufficient, or which are the features which we're actually missing? And here I just want to briefly show two features that one actually misses. One is the K-dependent orbital composition of this J-effective 1/2 band. This is something you can investigate with polarized light in ARPIS experiments. Thereby you highlight certain type of orbitals and can investigate the composition. This you would actually miss if you only consider a one orbital model. And this is also confirmed with DFT calculations, which show that you should consider actually multi-orbital or 3-orbital model in order to incorporate these effects. Another important information which we would miss is actually the magnetization density, or an explanation for the magnetization density. This is something you can address, for instance, via polarized neutron diffraction. Because this is not a perfect antiferromagnet, but it has a slight canting, you have a very tiny ferromagnetic moment that you can use for polarized neutron diffraction in order to reconstruct the magnetization density. So if you do this, which takes a lot of time, you have to measure 180 breakpoints in order to reconstruct the magnetization density that I show here. You observe that is actually counterintuitive to a local J-effective 1/2 picture, in the sense that we see here around the green points, which are actually the iridium atoms, that the magnetization density has rather a dxy shape and not the isotropic shape that I show on the right, which would be the kind of naive expectation from a very local J-effective 1/2 orbital. You also don't see any oxygen moment, so no magnetization density around the oxygen atoms, and this orbital is very extended. So this means that you cannot really describe the magnetization density nicely with a local J effective 1/2 state only, and this also means that you should go to multi-orbital models in order to incorporate these effects. This is already the end of my talk, actually. So I would briefly like to talk to thank my collaborators. This work that I've shown was done in the last years in collaboration with Cyril Martins from Toulouse and done in the group of Silke Biermann at CPHD at École Polytechnique. The experimental results that I've shown for ARPUS were mainly done by Alex Lois and the group of Véronique Broé. And we also have a collaboration with a neutron scattering group of Philippe Bourges. There it's mainly Jae-Hong Jeong who did the experiments. With this, I think I will leave you with my summary, and I thank you for your attention and look forward to your questions.
Right, any questions?
I have a naive one. You say I'm not totally an expert on that, but I mean, can you comment about the use of the Gutzwiller ansatz?
Okay, Gutzwiller ansatz was used very much, and in particular, if you look into the reviews of DMFT, this is also one of the techniques which is used for comparison. However, here for these kind of dynamical features, it's not used. So, I mean, the central point.
But you could, right?
In principle, one could use Gutzwiller wave functions. Yes, sure. However, here, I mean, we want to have this dynamical feedback, which means that we have really lifetime effects for the spectral function. In other words, this dynamical coupling of the side, or for us, it's the cluster, to the electronic bath will introduce a lifetime aspect for the electrons. And this is something which is very difficult to get by other techniques, actually. And so this is the strength of DMFT. And once again, the other strength is, of course, to successfully describe the full transition from a weakly correlated metal to a mod insulator. Yes.
Any other questions? I was wondering how you have the U and J in the Hubbard model, how they are related to the spin coupling.
Yeah,
because
that's a very good. Yes.
Sorry.
It's a very good point. So let me just present it here. So it's true that we have the spin orbit. Exactly, we have U and T for the Hubbard model. You don't explicitly have the spin orbit coupling. This has to do with the fact that we already included the spin orbit coupling on the when doing the DFT. So what you see here for the spectral function, for the electronic structure, is already including the spin orbit coupling. So afterwards, we map onto a tight binding-like model by using Wannier functions. And in terms of these Wannier overlaps, we can define hopping parameters. So think of these T's as already including the information of the spin orbit coupling. But you're of course right that we lose a lot of information here because we map onto a one orbital model. And this is also one of the reasons why I showed in the very last part, why it's important to go beyond that. Yes.
Thank you. Any other questions? So there has also been some study on strontium glutamate, is it?
Yes, so there's also a lot of studies recently on strontium ruthenate. Strontium ruthenate is a bit less correlated in the sense that the U and the spin orbit coupling differ a bit. Okay, it's very interesting, yes, and there has been a lot of research on strontium ruthenate. There, the question is also, I mean, first of all, you have 3 sheets of the Fermi surface and not a single one. So you really have 3-band physics, which is important. And there are also very interesting studies, mainly by the group at the Flatiron Institute in New York very recently, who combine DFT and DMFT to have a look at this problem. So this is a very related and similar technique that is applied there in order to investigate this material. Yes.
Any other questions? I don't see any. Let's thank.
Just one quick question. Sorry,
yeah.
Just to have an idea. How long does it take to do the numerical calculations?
Yeah, good question. This very much depends on the solver you use. So I think here I just mentioned a few. The costly part is actually the solver.
Yes.
So one of the standard techniques that one uses nowadays is continuous time quantum Monte Carlo, and this is actually very expensive. It depends on the temperature at which you perform the calculation. It also depends on the so-called fermionic sign problem, which is causing main headaches here. But you can resort to other solvers. For instance, we also used a cluster generalization of the Hubbard-1 solver, which effectively decouples bath and impurity, and then you have a rather cheap solver that you can employ rather fastly. However, for typical calculations for CTQMC, this can easily go up to perhaps 8 to 10 hours for one iteration on a massively parallelized calculation. So recently we were doing calculations for a cuprate where we had 8 to 10 hours of computation time on 100 CPUs just for one iteration of the DMFT loop. And then you have to iterate between 10 and 20 iterations. So this takes quite a bit of time, but it increases, the computation time increases really rapidly with the inverse temperature. So the lower you cool down, the sooner you hit the sign problem actually. Yeah.
Right. Any other questions? If not, let's thank our speaker for his excellent talk. We can proceed with Ari.
Okay, while I'm setting up the slides, I don't know if you have already obtained, participants, if you have already obtained the link to download the slides. So it's foreseen that you can download them. So in case you didn't get it, I included at the bottom, I included the URL where you can download the slides if it doesn't disturb listening to my talk too much. So there's the URL at the bottom where you should be able to download the slides. So my name is Paavo Seitsonen. I'm working at the École Normale Supérieure now. Like Marco showed this morning, I'm originally now a chemist, but to be honest, I studied physics and I was earlier at the IMPMC where Marco is now. And well, now I'm doing actually many other things related to DFT, but for this talk, I chose a topic which I studied when I started to do my PhD in Berlin, Fritz-Halm Institute. So that's applying DFT methods on surfaces. So again, this will be quite applied talk. I will not go into the details in any respects. I will try to kind of give you an idea what we can do with DFT and on surfaces. This will be on surfaces of solid materials in my talk. And just if in case you happen to come to Paris and you want to visit us, you might recognize this building. Then on the left, I hope you can see there's the golden cupola of the Les Invalides. And the next small peak would be Panthéon. And our campus is actually called the Campus Panthéon. So we're very close to the Panthéon. So it's a small hill, quite central in Paris. And well, we're not also far away from the Sorbonne University. And in case you have heard about École Normale Supérieure, maybe that was on the original paper of the Hohenbeck-Kohn paper. So that's the foundation of density function theory. So it's not yet the Kohn-Sham paper, which appeared 1 year later in 1965, but this was in 1964 when Walter Kohn was visiting at the École Normale Supérieure. Well, then he went back to the US and continued there. But this is part of where the history of DFT was made, the École Normale Supérieure. So a short overview of what I will talk about. I will very quickly talk about the history of calculation of surfaces with the DFT. Then I chose two examples. One of them is an old one, basically that's what I was doing when I was still in, or I studied when I was still in Berlin. And then another one is recent work on supported hexagonal boron nitride. And a very short perspective, if I have time, it's only one slide. So about the history of the calculations, you can see that if the DFT was introduced 1964, 1965, the first kind of applications of DFT on surfaces was made already a few years later, which is quite interesting. But what the authors had to do, they had to go to quite specific approximation, which is the so-called Jellium. So it's basically replacing the surface with the one-dimensional model. So you lose the information about the atoms. So this is how it looks in practice. On the left-hand side, you had the material, and it's described kind of the nuclear background is replaced, or the nuclei is replaced by a positive background. And then you have the electrons, which follow the Duchamp equations, and the electron structure is a result then using the density functional theory. And this is just two different values of densities of the electrons. So using the so-called Wigner-Seitz radius. So one sees, for example, these Wigner-Seitz oscillations inside the material. And then this side is the vacuum. And one sees how the electrons, to avoid infinite kinetic energy, they smoothen. And this, of course, leads to also to these Wigner-Seitz oscillations. So this is kind of small things which people could do. Then some quantities which they could extract is the work function. So again, if on the left-hand side, there's the material, on the right-hand side, we have the vacuum, and the potential, here the effective potential converges to value. And if we take the difference of this potential far away, or in principle infinite distance from the surface and the Fermi level, we obtain a quantity called work function, which is in principle a quantity that can be measured experimentally. So that's corresponds to the energy that an electron has to do, or the energy the electron has to gain to be able to escape the surface. So it has to go uphill in the potential. So this is a quantity which relates the experiments and the outputs that we can get from DFT. Then, well, to be honest, this Jellium model, it worked pretty well. In the case of the alkali metals, so this is now again the Wigner-Seitz radius corresponding to these metals. So these are, of course, nearly free electron metals, but then it failed already. So this is the dashed line. It failed miserably in the case of more, well, let's say traditional metals, so aluminum already. So this is the surface energy, and it should be positive, of course, but the Jellium gives a negative surface energy, which is, of course, unphysical. So this is some quantity where the authors then they had to introduce some kind of the lattice, and then they could recover more or less these values. But this was, you see, also pretty simple elements that they could handle. Well, I took the example, as I already mentioned, when I was doing my PhD in Berlin. This is a long-time collaboration, which, well, it hasn't continued anymore in the last years, but I was just in contact with Herbert Over. So he's one of the experimentalists with whom I have collaborated over the years. So I have been collaborating with experimentalists, lots of surface experimentalists over the years. And many of them, actually, they were working, or some of them were studying at the Fritz Haber Institute at one of the experimental departments, the one of Gerhard Ertl. So that's on physical chemistry, and Herbert Over was a group leader at the time at Ertl's department. So now Herbert has moved to Gießen in Germany, and Gerhard Ertl, well, he's retired, but I met him still 2 years ago at the conference. So he's still, well, at least following science. So this project is about the catalytic activity of ruthenium, and the starting material is the metallic ruthenium, so ruthenium 0001. That's one surface orientation, the preferable surface orientation of a metallic ruthenium. So ruthenium has HCP lattice, and this is the preferred direction. So what was known about CO oxidation, the catalytic oxidation on ruthenium in the mid-90s, was that it was a poor catalyst when there was a low oxygen pressure around the surface. But it turned into an excellent catalyst at high oxygen pressure. And the origin was not known at the time when I was, well, in Berlin. So then also Herbert was studying with his group this material and tried to conclude where did this difference in the catalytic activity come from. And we had, as I mentioned, long time collaboration. And in 2000, well, beginning of 2000s, we managed to publish the results, the main results, and that's a kind of qualitative change on the surface. So nowadays it may sound trivial, but at the time it was really new, because most people thought that when you depose lots of oxygen, so you have a high oxygen pressure, you just put oxygen atoms dissolved in the subsurface layer. But the metallic ruthenium, otherwise it's covered with oxygen, but nothing changes there. But there was the problem that first of all, the oxygen could not dissociate anymore when the ruthenium was already catalyzed, covered with oxygen, or it was very slow dissociation. And the CO in a Langmuir-Hinshelwood kind of catalysis, the CO should first stick to the surface, but it doesn't stick when the surface is covered with oxygen. So the problem was resolved, or this discrepancy was solved in the activity by realizing that the ruthenium actually it's oxidized, so it turns into ruthenium dioxide at the surface. So in this image, which is an experimental image using the so-called scanning tunneling microscope, so STM, on the right, there's still the metallic ruthenium covered with oxygen. So one sees this hexagonal pattern, but on the left, well, this is just, these are two zooms into the main image. So on the left, we see these rows and these protrusions, and that's actually the ruthenium dioxide. So that's the Charconal system, and the preferable direction there is the so-called 110 direction, which exposes some atoms towards the vacuum or towards the reactants. And so this was the origin or our explanation of the change of the catalytic activity. So the ruthenium gets oxidized, and it actually provides sites also for the CO to absorb. Well, we used DFT calculations, or I did DFT calculations at the time. So we used the so-called slab geometry, where we have some slides, some layers of the surface, and then vacuum. So we use the periodic boundary conditions, so we have to have enough vacuum and so on, but these are technical details. So what you see here is this top direction of the surface. So you see the outermost ruthenium atoms and the outermost oxygen atoms, and then toward the bulk in the middle. So that's where the electron structure is more or less like the bulk. So it's of course a finite size, but we see that very soon the electron structure approaches that of the bulk material. So what is shown here is a kind of electron density difference. So we analyze the electron structure, which we get out from the DFT calculations, and we see that the electron structure around the surface atoms, so here the ruthenium and the oxygen, it changes. And it actually, this ruthenium, well, it has the notation also, so-called one-fold coordinatedly unsaturated ruthenium atom. So it's missing one neighbor, the oxygen which in the bulk would be above it has been removed. So this is the sites where, for example, CO adsorbs. So here, these are just schematic illustrations using well, local geometries from the DFT. But I must say that at the time, also the calculations were limited to some tens of atoms at the computer resources. So This was yeah, about 20 years ago. So this was what we could do at the time. So then just quickly about the reactivity. So in the experiment again, so when they deposed the CO on the surface, they see these bright spots on this ruthenium dioxide surface. So those are, of course, the adsorbed CO atoms. And when they heated up the system and provided some oxygen, they saw after the reaction that there was some grooves and metallic particles of ruthenium. So that's happened when the CO, when it became oxidized, it took some of the oxygen off the surface with it in the reaction. So then it consumed the oxide. But in the real world, one would all the time also provide oxygen, so it would actually heal the surface and the ruthenium would remain oxidized. So in the DFT, one could also simulate this. I don't have example here, but one could also simulate these STM images. And the so-called Thermoelectric model is the most popular used model. It's very simple, actually. It's just post-processing a little bit the output of the standard DFT calculations, and you can compare the experiments. Well, another quantity which can be compared directly to the experiments is, of course, the geometry. So when we optimize the structure, we try to find the geometry which gives the lowest energy possible in the system. And this is on top, it's again an illustration of the system. So here we instead of having the CO, we have the so-called on top oxygen or gamma oxygen. So where we, from the oxygen gas, which is deposited on the surface, that dissociates, it can dissociate easily on this oxide. So we get this on top oxygens. And this actually fills the coordination of the ruthenium atoms, which were originally unsaturated when we cut the surface. And then we could compare the experiment in this called, so the method is the low energy electron diffraction, and then the DFT. So we can directly compare the values which they get from the experiments, which requires actually some modeling also, and the DFT values. So we get reasonable agreement, not as good as maybe Mauro promised. So, but within a 0.1 angstrom, we get the agreement. So this is a quantity that we can compare. Other methods, well, if I manage in the second part, I will mention some X-ray standing wave experiments, X-ray diffraction, then atomic force microscope, and well, the STM usually cannot be compared very qualitatively, but quantitatively at least. So again, we need to model it in DFT, and then the outcome is not exactly what the experiment gives, but we can do something there. Of course, another quantity what we get from DFT, because it's also a so-called total energy method, is the energetics. So we can calculate energy differences, for example, adsorption energies, reaction energies. We can calculate adsorption energies, reaction barriers, and so on. Then if we go to the more advanced methods, we can also calculate free energy differences, so at finite temperature, finite pressure, and so on. So here I just give an example work again, which we did with Herbert Over and the colleagues, was the catalytic oxidation of hydrogen chloride. So this is a product which is a result from many chemical reactions, but this is actually not how the chemical industry wants to have it for when they want to use chloride. They want to have chlorine gas. So we can use ruthenium dioxide to catalyze HCl, this chemical diagram, into chloride gas. And this is what we did. So we get some reaction energy. So in this case, they are kilojoule per mole. So when we divide by more or less by 100, we get the energetics in electron volts. So this is something we can calculate, energetics from the density function theory. And it cannot be directly compared, but at least qualitatively, it can be compared or using some modeling with experiments. So here I saw an example of the so-called temperature programmed reaction. So when the experiment is they deposit the molecules on the surface. So in this case, it's the HCl and the oxygen. And then they heat up the system. And at some point, the reactants are able to overcome the energy barriers, so the free energy barriers in that case. And then one can measure what comes out from the experimental cell. And here they saw the production of HCl. So there's a peak at around 530 Kelvin. So this again, where we can compare, maybe not that directly, but at least we have some comparison between experiments and theory, DFT. So another thing which has been used in this specific case also is to use kinetic Monte Carlo methods. So we need the parameters from somewhere, from experiments or DFT. In this case, most of the parameters were taken from theory. So these are 3 different sets of parameters, and then the experimentalists, they did the modeling of kinetic Monte Carlo. So that's kind of a lattice model. So they model where, for example, oxygen adsorbs, where there's CO adsorbed, and then the reaction. And then all of these, they follow energy barrier. And then one can model the real catalytic output. This has been done in many cases. So in this case, this was collaboration with Herbert Over, where they then compared the experiment. So you might say, okay, the agreement is not that good. It's 1 order of magnitude, but these are all quantities, or these outputs, which is here the turnover frequency or the catalytic activity. That's really a quantity which depends exponentially on the energy barriers. So tiny error or in an approximation in the model, and you get the large difference in the output. So we were happy that at least we get already a qualitative agreement. One thing which is maybe obvious, we can calculate the vibrational frequencies and maybe go beyond. Well, in solids, they would be called phonons, and compare with the experiment. So this is just an experimental spectrum where they use the so-called infrared spectroscopy to measure the absorption of infrared signal. And when there's absorption, there's a dip here. And then these were 3 different systems, and this corresponds then to the vibration frequency in the system. So we can calculate, at least at the harmonic limit, these quantities also. I don't have any examples here, but this can be done and has been done also in the case of ruthenium dioxide. Another example I take is the experimental methods. They are, for example, X-ray adsorption. So the so-called XANES or NXF method defend the same thing called by a chemist and physicist. So here one radiates the system, the core levels with X-ray photons. Often one has to go to the synchrotrons in the experiments to get enough intensity. And then when one gets, if the energy is high enough, one gets deposited photoelectrons, so the effect of Einstein. And one can then obtain the energy of that core level. So in this case, M. One can do also in the case of, so this would correspond to the X-ray photoemission spectroscopy. One can also look how then these electrons, when they are excited, how they are absorbed by the valence states. And this is the method of XANES and NXFs. And this can also be calculated. It was actually a colleague at the time also at IMPMC when I was there, Matteo Calentra, who developed this in one of the DFT codes. Then we can get a magnetic response, which is basically the XAS.
Sorry, you have 5 more minutes.
Okay, thank you. And then we can have use also methods of lower energy electron microscope, but there we don't get atomic resolution. So those are the experimental methods. So this is just an example of the XPS. So we get the information in the experiments. So we get the information on the binding energy of those electrons. So what I showed here with the N. So we get the information at which chemical environment that atom is. So this is atom specific, because the core levels, they of course are different atomic species, but also they depend slightly. Here you see usually on the scale of tens of electron volts up to a few electron volts, they depend on the chemical environment. And this is something which can be compared to DFT calculations using the so-called initial state approximation or the full or self-consistent calculation. So again, a quantity that can be compared. So I want to quickly mention the second example. So this is HPN on iridium. So the hexagon boron nitride, well, if you don't know, it's like a graphene lattice, but you replace every second carbon atom with boron and every second with the nitrogen. So it's a honeycomb lattice, threefold symmetric. And here we use the iridium 111 as a substrate, but it has been grown on many different metals. So this is the so-called supported system where we use a solid surface to support the HPN. So why HPN? Well, it's an interesting material because it's insulating. So that's a difference, of course, to graphene, which is a semi-metal. So nowadays, people use often HPN to isolate, for example, adsorbate molecules from the metallic electronic structure of the support. Well, this project was not that detailed. This was about kind of going to the limits of DFT or the approximations. So Marco mentioned the exchange correlation energy or potential. And until now, there's no explicit expression of that term. So we don't know exactly how the term looks like, except for some limiting cases, and the exchange is known. But in practice, we have always had to approximate this. And then we have to choose a good one. And we use this model system of HPN on iridium because we have both strong directional bonds of mainly the nitrogens forming with the iridium. And then we also have so weak van der Waals interactions. So now we have an interplay between strong and weak interactions. And then depending on the exchange correlation, we might describe the system better or worse. And then we want to compare with quantitative experiments. So here the experiments were Peter Liljeroth, who is a professor at the Aalto University in my native Finland, and Fabian Schulz was a PhD student at the time. Now actually Peter recently he moved to Fritz Haber Institute in Berlin, so kind of circle closing. So this was published last year. And like I said, it's an experimental study combined with DFT calculations. Well, from the experiments, here you see this is the moiré structure, which was mentioned before. If you are not familiar with moiré, that's a kind of periodic structure, but the periodicity is not the implicit periodicity of the HPN in this case. The periodicity is about 10-11 units of HPN, and then you have a periodicity with the substrate. That comes from the different lattice constant of the HPN and the iridium on the in the lateral. And then what they measured here in this case, atomic force microscope, was the corrugation, so the height between the spots here and here. So this is something which can be measured in AFM, maybe not many other things quantitatively, but this they can measure quite well. And then what we did in this study, well, here are details from the DFT calculus. You can check nowadays, you can see that we can go up to, well, like Marco said, about 1,000 atoms. And this is the final geometry, which we found from the DFT calculus, actually with one approximation. So in the side view, I don't have time to go to the details, but in the side view, you see that we have these regions where the nitrogen sits on top of the iridium atoms, or the outermost iridium atoms. And the other regions where the nitrogen is not on top, the bond is weaker, so it's more like the van der Waals interaction. And then we get this difference in the height or this corrugation. So this comes from the moiré, that we have different so-called lateral registries in these parts and the other parts. So the color code here is the height. So that gives the moiré or the corrugation. And then what we did was to indeed, I used many approximations of the van der Waals, and then we tested also something like K-point sampling and so on. And we compared the experiments. So here the experiments, one of the experiments is the dashed lines. So we wanted to have an approximation which gives more or less the dots, which are the height of the boron and nitrogen atoms. So for example, this approximation here seems to be doing pretty well. And then other approximations, they give either too little corrugation, some of them too little corrugation, and it's too far from the surface. So depending on approximation, we get different, even qualitative difference. So then we want to use this study also to choose the approximation which we want to use in future calculation in similar systems. It's not a solution to use in all systems, but this kind of more structures, we're going to use these approximations. So I'm running out of time. I just mentioned here we did some STM calculations. So here the experiments. This is actually not the two-dimensional view. These are just some line cuts using different bias on the STM, and we could reproduce qualitatively here with this Telsov-Hammar model. We could qualitatively reproduce the experiments. Then XPS, well, unfortunately, I don't have time to go into details, but again, we see kind of the effects in the DFT calculations that is seeing the experiments. It's not that good, the agreement, but we get qualitatively the same effect. And then the last slide, I just want to say my overview for the future. I haven't done any of these myself, but for example, Dirk Hammer, who is in Denmark, he was actually a postdoc shortly, we overlapped in Berlin, and he has been active in supporting the machine learning in the surface structures or on the surface physics. There are already studies where people use these methods, so machine learning, they fit the potential in the surface of the adsorbates on the substrate. For example, in this case, they were interested in the atomic structure of these oxides, how they are, which kind of structures they form. And they use the machine learning. So one teaches the potential, and then with this one can accelerate the search for these structures, because in DFT otherwise this would take too long time, because it might be very different structure than what we have in mind. So using this kind of machine learning potential and then intelligent algorithms, we can then use more and more, for example, study the surface systems. So with this, I'm badly over time, so I will thank you for your attention.
That's it. Thank you. Right, any questions? We have some 2 minutes, I think, for question and answer. So Ari, do you want to talk a little bit more about how you use machine learning in such?
Well, I mentioned I'm not using that myself, but what I have followed the field is that indeed, also when we do the calculations, often we had to relax the system. So we get information when the atoms or the molecules, whatever you adsorb, how that interacts. So then this is the kind of part of the trainings that one can use. Of course, if the structures are very different, the coordination, for example, is very different than in the structures. So we have to choose some kind of artificial structures. So we don't take exactly what we expect the structure to look like, or the known structures, but we take some arbitrary structures. But of course, we do DFT, like Marco also mentioned this morning. We can use it in principle, well, in principle, almost in any kind of geometry. So the more different geometries we take, the better we get sampling of the energy surface. And then, well, of course, at the end, one always wants to use DFT to really look if the structure given by the machine learning is stable. And then one can calculate the surface energy and maybe other quantities if there are experiments already available, and compare the kind of quantities which I mentioned before. For example, you can calculate and compare with the experiments to see if your structure, which you got with this machine learning, is or corresponds to the experiment. So this has been used actually recently. I saw another work, one of the materials, phosphorine, So another kind of two-dimensional material metal surface, that there they actually result the structure using the machine learning techniques. And it's similar strategies. So you put in structures calculated with DFT, hopefully many of them, and then you try to conclude the potential from that, and then use that in the structural search systems or software.
Right. Thank you. Any other questions? In Singapore, I think everybody is getting hungry because it's close to dinner time. But still, science should come first. Any questions? Right, if not, any questions? I don't see any. Yeah, it's pretty exhausting as well sometimes. Unfortunately, you are placed at the back of the program, at the end of the program. So, yeah. Okay. Thank you very much. Yeah, thanks, Hari. And we call upon our last two speakers. So that's going to be Masha and Kedar. So each one of you get 10 minutes or so, I guess.
Something like this, yeah.
Minutes. Yeah, okay.
10, 15 minutes, yeah.
Yeah.
Good evening. So it will be quite a different presentation because it's will be mainly only experimental results. And so, but let me start. So I'm working in NTU in Singapore, and I'm mainly working on electron microscopy. So I will show you a few results that I think are relevant or can be relevant for simulations or DFT simulations, at least few of them. So let me first introduce what is electron microscopy. So I'm not sure how familiar you are with that. So on the left-hand side, you can see a TEM. So it's a machine which is something like 4 meters high. We have an electron gun at the top of the machine, which is used to generate electrons, and the electrons are accelerated at depending on the setting, but up to 300 kilo electron volt nowadays. And on this machine that you can see, so this is the one which is installed in NTU in FACS. So you accelerate your electrons. You have a condenser system that is used to form the probe. Then you have a chamber when you have to put your specimen in here. You have an objective lens around the specimen, and then you have a set of lens below the specimen to record an image. What is special about this microscope is that this part is a probe corrector. So it means they can correct for higher the aberrations in the condenser system and then remove the aberrations on the probe forming system. So thanks to this probe corrector, we can get beam size down to 50, 60 picometer. And when we use a TEM in STEM mode. And on the bottom part, this element is a probe corrector, image corrector, sorry. So it corrects the aberrations when we are in TEM mode or when we are in a plane wave illumination. So, and using this image corrector, we can get a resolution in the image down to like 50 picometer, and we can measure atomic displacement down to a few picometer on a good day. So this is what the TEM is. And then at the bottom, so the part that you don't see, we have a variety of detectors which can detect a few signals. So I put the different signals that can be recorded in a TEM or in a SEM, and then I will explain later why I did so. So on the top of the specimen, so this is your specimen. On the top of the specimen, you have the signals that can be recorded both in a TEM or in SEM because they are emitted on top of the samples. I won't go through these signals right now because that's not the one I'm going to talk about. Just so secondary electron signal is the one used in the SEM, and you may have heard about EDX, which is used for rough quantification of the composition of the specimen. But what we do in TEM, so in transmission electron microscope, we record the signals which go through the specimen, And we can classify the signals in 3 categories. So we have the coherent elastic scattering. So it means that there are electrons which didn't transfer any energy through the specimen, and they are still coherent one bit compared to another. So we have kind of interference signals. We can also have some elastic scattering, but incoherent, which are incoherent between each other. So this signal is mainly used to get atomic composition, and the signal from the incoherent elastic scattering is kind of proportional to the atomic number square, or something like this. And we have the elastic scattering. So these are the electrons which has lost energy when going through the specimen. And so we can go to what we call electron energy loss spectrum, and we can get some information about the local atomic surrounding of the specimen. We'll come back to this one later on. So let's start with this slide. So this is a study that I did some time ago, but was only published recently. So what we did, we use coherent signal to measure the to get such an image, and using this coherent imaging, we can get a different contrast depending on the local crystallographic structure. So we have R and R prime domains in the ferroelastic bismuth iron oxide. And what we want to do in this ferroelectric, we want to study the interface between the different domains. Because what is really interesting on this ferroelectric material, we can move the domain by applying some stress, or we can also displace the domain by applying some electrical voltage. So by doing some electron microscopy, we can measure the stress inside the specimen, and in the same time, we can record information about the local atomic configuration using the inelastic scattering. And we have seen that we can measure the different signal between the 3 different phases, which represent in the specimen the R phase, the R prime phase, T and T prime phases. And when we compare the spectra that we got to the one which has been obtained experimentally, we can see that we have quite a decent match. So we are quite confident in the phase that we have been able to observe. This type of measurements has been done at relatively low magnification. So typically the size of a domain is 50 to 100 nanometer, because when we increase the magnification or the resolution, then we change the configuration of the local ferrochromagnetic domains. This is one example. So I would just go through a few examples. This one, it's to see the highest resolution that we can get by using the incoherent elastic scattering. And so it's a paper that we have submitted recently. So my colleagues have measured the ferromagnetic resonance signal for YAG grown on different directions, and they have shown that depending on the growth directions, they have different ferroelectric signals. And this was possible because the epitaxial growth of YAG on top of GGG substrate was perfect. So you can see the interface, and you can see that there is no a defect at atomic level, and we can almost don't see the interface between the GGG and the YAG. We just get a contrast difference because the average atomic number is different, but there is no crystallographic defects. And now for the rest of the talk, so a quick presentation, I will discuss 2D materials. So just also basic stuff that we can do with TEM. So we can exfoliate the 2D materials. We can make devices, and we have nowadays 2D materials which are ferroelectric, ferromagnetic. And I'm quite interested on the first of them, on the ferromagnetic one. So what we can do, so in primary, we can take STEM image. So taking the incoherent elastic scattering, we get different contrast. We can know which elements are where. So depending on the intensities, we can know either tungsten or the selenite or diselenite. So in this case, we can see that one atom of selenite is missing. Then we can have some substitutions, and so on and so forth. Not really fun. So let's go now in more interesting studies. So when we use different signals, we are not only sensitive to the minimal potential, which is the electrostatic field created by the atoms, but we can also map the magnetic domains. And it is what's called the Lorentz TM microscopy. So what we can do on 2D materials of FGT, didn't write it down, on this FGT material, so we can take a Lorentz image, which is sensitive to the magnetic domains, and depending the temperature at which we record the image or the magnetic field applied to this while we record inside the TM, we can have a different magnetic structure. So we go from a lamellar structure at low temperature when no field are applied, and by increasing the field inside the TEM, you can see that the lamellar structures goes into Iceland domains. And now the next step is to follow the propagation of these domains when we apply different stimuli. I want to also introduce this paper because it's a paper made by a colleague quite some time ago already, and at the time it was really quite.
Yeah, you have the minute.
Sorry, 10 minutes more?
No, the 2 minutes.
2 minutes. Ooh, lolo, it's fast. So I go fast. So yeah, what I like
Oh,
about this
you
paper.
can eat into Kedar's top.
Okay, so what I want to show on this slide, that the guy was able to image these atoms with a different contrast, and so it's brighter, so it's a different element. He has identified that it was silicon, but what we don't know the local coordination of the silicon atoms on the graphene lattice. And by recording some elastic signal, so which is more or less what the EXAF fine structure, we can know if it's a 4-fold coordinate or 3-fold coordinate, a planar, or if it's coming outside of the graphene layer. So by combining the incoherent imaging mode and the inelastic mode, we can identify the foreign species, and we can also get information on the local atomic coordination. So maybe this slide, I think, may be of interest. So this is relatively a new paper, so a new field of TM microscopy. So what we can do, we can also measure the electrical potentials, which is in between the atoms. So we do scan our probe through a 2D material. It was MOS2 in that case. And then by looking at the shift of the probe when we scan the specimen, we can directly measure the electrostatic field in between the atoms. And so what you can see in this image on the left-hand side, you have a B layer of MOS2. On the right-hand side, you have a monolayer of MOS2. And the image, or the colors that you see on this image correspond to the electric field between the atoms. And then so we can know the distribution of the electric field depending on the atomic positions. And from the electric field distribution, we can then get the charge distributions and so on and so forth. And I just go on the last slide before the time is over. So if it wants to go, oops, this is the last slide. And on this last slide, so we wanted to study the interface between silicon carbide and graphene. So they grow the graphene at really high temperature, like 1000 degrees. And there have been a lot of DFT calculations to know about the reconstruction of the silicon carbide surface and about the composition or about the structure of the first layer of graphene. But what we can do in TM, so we can make cross-section, we can record a variety of signals, and one of them is electron energy loss spectral through the interface, and then we can see that we start from silicon carbide, we have contribution of the pi and sigma orbitals, and when we go deeper into the graphene, the pi orbital contribution decrease, and we mainly have a sigma orbital contribution. We can also quantify the amount of carbon over the amount of silicon, and then we can use this quantification that we got from TEM as input for DFT calculation to get back information on this buffer layer, which is in between silicon carbide and graphene. It's still ongoing work. And the last sample, if I may, the last slide, if I may, it's high temperature measurement at atomic resolution inside the TM. So it's also on MOS2. And then we follow the growth of the facet inside the TEM at different temperatures. And we have been able to see that depending on the temperature we used, we have different age reconstructions, and we can also estimate the growth rate of the pores and the growth rate of each of the edge, if you want, by studying quite a variety of samples. I thank you for your attention, and feel free to ask any question if you have some.
Right. Any questions? Merci beaucoup.
De rien.
I just have a quick question. Okay. Is it possible to change the pressure or not?
Yes, it is. So the base pressure is something like 10 to the minus 5 Pascal. But we do have, there are two ways to change the pressure, in fact. In NTU, or the most common way to change the pressure is to use a cell, if you want, in which we can enclose the specimen and put some gas inside. There's such a cell in NUS, but we then limit the resolution to a few angstrom. We cannot go maybe 1 angstrom for really heavy elements. And the second approach, it's to use what it's called item, and there are maybe 4 or 5 items worldwide, one in Lyon, by the way. And in these microscopes, we can put up to 10, 15 millibars, and we can still get really high resolutions. But we are limited to relatively low pressures as far as material science is concerned.
May I pose a question about the graphene on silicon carbide? So
Yes.
it's the current model that there are actually some silicon atoms also in this so-called buffer layer or the zero layer.
Yes,
So
yes.
It's some kind of alloy of the...
Yeah. That's clearly the case. But my main concern when I read the previous publications is that people consider that the silicon carbide, even the last layer of silicon carbide, was still stoichiometric. And it looks a bit strange in the sense that that it's grown at really high temperature. So I would expect a gradient of silicon and carbon. And what else? Yes, and this variation of the composition in the silicon carbide will then affect the atomic rearrangement of the last layer of silicon carbide, and may also affect the local coordinations in the first layer of graphene, in the buffer layer. So yes, there is kind of a gradient of concentration, but they are really, I'm not sure, in the first layer of graphene, so after the buffer layer, it may have maybe a really small amount of silicon, but the gradient in the silicon carbide is quite high. So it's not a sharp transition.
Okay, thank you very much.
Welcome.
Interesting.
Any other questions? If not, then maybe we can call upon the next speaker. And at the end, you can still ask questions.
Okay, I stop sharing.
All right. Good evening to everybody in Singapore. Thanks for waiting till the last call. I appreciate your attention, and hello to everybody in France. I appreciate the organizers for giving me an opportunity to present, and I'll be quick and I'll make it entertaining because it's the last talk of the day, right? So I put a pretty picture up here for everyone to start staring at. My name is Kedar. I'm a colleague of Marshall at NTU in the material science department. And I'm actually using a lot of high performance computing data for a data-driven approach. And at least the initial emphasis of my work is to study thermoelectric materials because they're very interesting, both from a physics perspective and from a solid state chemistry perspective. It's quite a unique field where a combination of those two intersects, and then that leads to new materials design that actually allows you to discover new materials. So my work is a little broad. I work on one-dimensional structures, two-dimensional materials, inorganic, organic hybrids, But recently there is an effort that's ongoing here in Singapore for using AI in material science, which revolves around machine learning optimization, high throughput experiments, of course, high performance computing, which will be the focus of my talk, materials descriptors and database screening, and more, essentially, right? And so if you think about the scientific method that you actually use, discovery is at the forefront of how you actually make a useful product, right? So you discover a new material, for instance, then you go try to make it in the lab. You characterize the material. Typically, your success rate is like 1 to 10% if you're a very good scientist, right? If it fails, you go back to the drawing board, see what's wrong, try to make it again, and so on and so forth. And eventually you make the devices, you characterize the devices, and their success rate there is something like 1 to 10%. So you have 1 to 10% overall success rate to actually make a viable product, if you think about it. So AI and machine learning, AI is a fancy word, really it's just advanced pattern learning is how most people use it, is actually enabling faster diagnosis of devices, which I want to talk about today. Mostly in industry, we use quite a bit of work on automated process optimization loops beyond design of experiments. And I have some work there, which I want to talk about. We can also do AI-enabled faster synthesis, especially in the liquid form that you see over here, right? So that's completely possible, for example. But what I will focus on in today's talk is how this is enabling discovery, right? And that's really where the bottleneck for thermoelectric materials are. So thermoelectric materials are very interesting. The figure of merit of thermoelectric materials is ZT. It's a dimensionless number where the numerator is where you have an electron crystal and the denominator desires a glass, which is a phonon glass. So you want to have a highly crystalline material, but which is transferring heat like wood, for instance, or like air. So if you look at all materials that have been discovered, right, you can see that the ZT value doesn't go up very large. It goes from about 1 to 3. There are various different materials that are there, both in the inorganic space and the organic space. And typically a ZT of about 1 at a temperature of 400 to 500 Kelvin is about 10% efficiency. So a ZT of infinity, which is theoretically possible, is equal to the Carnot efficiency for any thermodynamic cycle. So the upper limit to this ZT is actually infinity, but there are very few repeatable experiments or theoretical predictions that go higher than 2.5 to 3. So the real game changer is how do we actually hit that thermodynamic limit of actually pushing up the ZT at very high values? And if you look at that equation that determines the ZT, the numerator is the Seebeck coefficient, which is basically the open circuit voltage. Let me get my laser pointer here. The open circuit voltage that's across a thermoelectric material under a temperature gradient. That's your Seebeck coefficient. The electrical conductivity is basically majority carriers. So typically the ZT is for majority carriers inside a system, which is related to the electrical conductivity, which, as you can imagine, has the right positioning of the Fermi level inside the band structure, and what is the energy dependence of the scattering of the charges inside the system, and the prefactor, which then determines your mobility. And your Fermi surface is very critical. For example, the band gap is very important. The initial effective mass is important. The deformation potential calculated from DFT is very important. So it's a very complicated structure. And that's just the right-hand side for the electronic properties, which is essentially the numerator of this ZT equation. There's a similar, branch that you can draw for the thermal conductivity, because it depends on both the lattice and the electronic property. And the lattice determines on the group velocity, the mean free path of the phonons, and the specific heat. And you can go further down and say, well, what is the real material component that determines what your ZT is, right? So it's a very complicated problem. So if you had to design a new thermoelectric material, what we've learned over 50 years of research is that you do a degenerately doped semiconductor and a very bad thermal conductor. And of course, you can go deeper into this. There are extrinsic and intrinsic properties over here, for instance. And if you go even deeper, what really is the element of materials design is how do you determine the right bonding of the crystal structure, the heaviness, lightness of the constituent atoms, and the semiconductor or semi-metallic or metallic compound that makes up a thermoelectric material, or whether it's crystalline, amorphous, etc. In addition, there are process conditions like microstructure and dopability, right? And those will determine what the material is. So what we did was we said, well, let's leverage on the ability of machine learning to predict from large swaths of data. And we looked at certain open source databases that are available today. And note that all open source databases so far, at least the ones that have large numbers of data in there about new materials, are all focused on ground state properties, right? You can calculate the electronic band structure reasonably accurately. Even that has many issues in all the open source databases there, like Materials Project, AFlow, Lib, for example, OQMD, etc. They have a whole series of ground state properties, but you can determine the descriptors of those materials, but they do have certain issues, which I will address at the end of the talk. But the problem of machine learning, if you frame it this way, is that you take each material and you vectorize it. So you make a mathematical representation, which is called the material descriptor. And then you want to predict certain outputs, right? And this is your whole machine learning problem. And when you want to get to a particular output, in this case, let's say the formation energy, which is a ground state property, you can take a whole series of inputs and link it to the output using a machine learning model. And the problem of inverse design is where you invert the arrow. Given a certain target output property, what new material will give you that property? And we use this to ask a question of what would be the next generation thermoelectric material. So since phonon properties are difficult to find on online databases, we focused on the electronic part, which is just the numerator of that system. It took us about 2 months to clean the data set. So what we did was we used Materials Project in this case. Many of you are experts in this, so you probably realize there are many issues with the Materials Project database. However, it's a good starting point, right? And then there are certain calculations that are done, which is bootstrap, which takes the ground state electronic structure, and based upon that, assuming a constant relaxation time of the charge carriers, calculates the Seebeck coefficient and electrical conductivity. There is an intrinsic assumption here, but at least it tells you what the functional property of that material is. All right. We then take it and in a JSON format, we flatten these 22,000 or 23,000 compounds, and we then create a whole set of data sets that determine that are based upon 3 different things: what temperature is the material at, what doping level the temperature is at, and whether the doping is p-type or n-type, for example. So this gives us a whole large data series. We use some filters, like for example, from our knowledge, we know, for example, that metals have a very low Seebeck coefficient because the asymmetry of the density of states is very low. And hence, we discarded those that have low band gap, which is actually turns out to be really good because as you can imagine, the low fidelity databases like Materials Projects are not very good at predicting compounds that have low band gap because of spin-orbit coupling. So we ended up with only 7,000 compounds or so that we used in the final database. There are many different ways of characterizing or vectorizing a crystal structure in a mathematical format. The one that was successful recently was to take a 3D structure. For those who are familiar, you might recognize the figure. This was done by Jeffrey Grossman's team at MIT at Boston. And you can take a 3D structure, and by establishing nodes and edges, you can then convert that into a graph. And once you put this into a 2D graph, you can then use convolutional neural networks to predict a particular output. So this is one methodology of doing this. There are certain improvements to this that have come to the fore in the last couple of years or so, but there are also certain problems. What we wanted to do was start with this to predict the ground state properties. But in order to predict your power factor, we do know that other things that are important features that you can get from the materials, such as the S fraction, the D fraction, the P fraction of the band structure, for instance, and other ground state properties such as energy above the hull, whether the material is stable or not, the density, the Fermi energy, band gap, density, etc. All those can be accounted for as well. And then the blue ones here are what we call discriminative inputs, which given an ideal material, if we could actually dope it and take it to a particular temperature, we can get a particular property, right? So this is what we added in order to predict our functional properties. And what you see here is a machine learning model. So for those who are familiar with machine learning, what you have on the y-axis is your prediction of a certain property, and given a certain tuned model, a machine learning model, and what you have on the x-axis is the actual values that's calculated from the database. So you can see that MIT CGCNN model, the crystal graph CNN model I showed before, has a very low absolute error. It can be improved at high values of Fermi energy as well after doing some sort of normalization. And for all crystal structure results, for the power factor, which is S squared.
Yes, about 2 more minutes.
Okay, 2 more minutes now, thank you. We can actually get a very good prediction with a median MA of about 8% or so. So not only do we get a good forward model, we can then inverse design a new thermoelectric material. So by identifying the right forward model that you can then put inside a user-defined input, and given a target power factor value, we can go back and come up with these new materials that the machine learning model has never seen before. So what's interesting is if you see this list that the machine learning model threw out, many of them are actually half-modular compounds within the cubic crystal structure lattice. And we know within the field of thermoelectrics that they're actually very good thermoelectric materials. Two of them have actually been reported with high fidelity electron phonon calculations before by the MIT group, Gang Chen. And so it is quite surprising because the machine learning was somehow able to figure out that a cubic crystal structure with a half-modular symmetry will give you very good electronic properties, for example. So we can actually use that. And the second thing you can do is derive some sort of chemical intuition, right? So you can figure out which features are very critical for you to get good values of power factor. I can talk about this further if you're interested, but I just wanted to end in my last 2 minutes with the challenges, right? So what I've talked about is the theory part, where getting the relaxation time, which is a constant relaxation time in all existing databases at this point, is quite a big challenge. So what we've set up to do in Singapore is we're building an electronic database. This is in collaboration with Deng Tianqi, Wu Gang, and Yang Shuo Wang at the Institute of High Performance Computing in A*STAR. And we started with 12 ABX2 compounds, which are known to be promising TE materials because they have lone pair electrons that gives you soft phonons that reduces the thermal conductivity. And we found through a study of these 12 compounds that polar optical phonon scattering is very important to get high mobilities. So we're able to predict the ZT of these molecules. And this was published in NPG Computational Materials sometime earlier this year. Now, what's interesting is this sort of workflow can be automated. So not only do we have a constant relaxation time, but we can calculate the full charge scattering times, given the full band structure and doing DFPT to get the full mobility. And we've done it for about 1,000 inorganic semiconductors at this point. So hopefully we can release this database in about a year or so, once we've actually analyzed all of the data. And then the whole concept is to have a high fidelity database that you can learn from, where the same framework that I had in the first part of the presentation, which is the DFT, the machine learning, can use a better database to learn from. And that can hopefully provide useful to the community. So with that, I'll stop and happy to take a few questions before we end the day.
Right, thank you. Any questions? Or for that matter, any questions to Marshall? You can ask both of them. Sure.
Sorry, I went really fast, I think. So hopefully you were able to capture what I said.
Is it possible to, instead of using computer to do convolution, is it possible to do it with some photonic crystal?
That's a good question. I haven't explicitly thought about it. In principle, yes, right? Because the idea of a convolution is revolving around how can you section a particular image, for instance, and not lose too much information. So it's sort of got to do with the sampling frequency at which you can get enough information out of it. So I think in principle, it's possible. I personally haven't seen anything where anybody have done this. It's a great question.
Other questions?
All right, thank you.
I guess everybody is just tired. It's not because the talk is not interesting.
So I have one.
Yeah.
Hi. So I'd like to ask you, I mean, the complexity of, if you like, the neural network machinery you used to be able to do this reverse engineering and get the meaningful and fruitful results out of it. So to go back from the material database and make the machine learn and find out finally the desired outcome. I mean, how complex is this, and how long does it take to make the machine learn the physical input? Yeah,
I mean, that's a great question, right? So honestly, in materials and the data that we have is not very large. So you actually, ironically, and I'll tell you this, you don't need to get the most complicated algorithms to actually run on them. You don't need very deep neural networks for you to learn from the current sizes of the databases that you have. There is a small caveat to that, is that if you really want to extrapolate out of existing databases to learn new knowledge, there is some evidence that neural networks are actually better at this, right? And so, but there's a small sort of offset. You need to have large enough data where you don't need descriptors and materials can be captured by themselves. And then the learning is more general and the neural networks are able to extrapolate. But we're not there yet. So that's why actually the results that we run can be run on an individual computer with a good RAM overnight, perhaps, but the hardest part is actually cleaning the data and putting it in a format which makes sense for us humans to interpret. Right? I think so that's the challenge. So when I even say interpretability, what it'll tell you is what features are important, but that's linked to the model and it's up to the scientist to interpret what you want to do it. I wouldn't say it's fully interpretability, right? It just tells you that there is some meaning to it and that these features are important. It won't tell you the exact correlation that'll give you the certain output, for instance. Thank you. All right.
Other questions?
I guess it's getting to be lunchtime in Paris now, right?
It's getting to be lunchtime in Paris and dinner time in Singapore.
Right.
For some people who eat early, it's already past dinner time.
Right.
Christian, you have no question?
Not this time. Too tired. My brain is fried.
Yeah, that's why I thought we are all fried. Anyway, we should thank all the speakers today for giving such excellent talks. And so let's convene tomorrow.
And convene.
Yeah. And also all the speakers today, and let's give them a round of applause. And then the other thing, of course, is that we'll convene tomorrow again at 3:30. Thank you.
Tomorrow, same time, 8:30 in France, 3:30 in the afternoon in Singapore. And we'll go towards chemistry more and more. So please. And it's going to be our last day, so tomorrow.
Yes, just the speakers, at least the speakers of tomorrow's session should sign in at 3 to check. Okay.
Or we tell Paris.
Yes, 8 Paris time. Okay.
Ciao.
See you. Thank you. See you tomorrow.
Bye.
Merci beaucoup. Bye-bye.